All right, big hello to my thermodynamicists out there. Let's start by taking a look at problem 1 from chapter 10. So here we go. And so this is 10.1 from the course text. Trying to scroll the page down a little bit. So A, how many degrees of freedom are there at the triple point of a pure substance? Okay. Well, that's a good question. So remember, the Gibbs phase rule is going to give us the number of degrees of freedom, or equivalently, the number of intensive variables that must be specified to fix unambiguously the thermodynamic state of my system. Okay, so in terms of how many degrees of freedom do I have? Well, F is equal to N minus pi plus 2, where N is the number of components in my system, pi is the number of phases in coexistence, and then 2 is 2. So in this problem, N, right, is 1. I have a pure component system. How many phases do I have? Okay, at the triple point, I have 3 phases in coexistence. I have a solid in equilibrium with the liquid and equilibrium with the vapor phase. So that'd be 3 plus 2. Okay, so how many degrees of freedom do I have? 0, right? And that's why I say the triple point of water is a common reference state, because just in saying that, water is at its triple point, the state of that system is already fixed. Okay, so A, I actually have 0 degrees of freedom. All right, let's take a look at B. Okay, so in B, it says, what is the fugacity of ice, solid water, at the triple point? The triple point of water corresponds to 0.01 degrees C and 0.611 kilopascals. At the triple point, water vapor may reasonably be treated as an ideal gas, such that FV is equal to Psat. Okay, and that's reasonable, because if Psat's 0.611 kilopascals, pressure is pretty low. Remember, atmospheric pressure is 101.325 kilopascals. All right, so that's, significantly smaller than atmospheric pressure. Okay, and so, it should be reasonable to assume that it's an ideal gas. So how do we calculate the triple point of solid ice? Any ideas? Well, the key here is that if I have 3 phases at coexistence, okay, then it must be that the fugacity of all of my 3 phases are equal, right? The fugacity of my vapor phase will be equal to the fugacity of my liquid phase, which will be equal to the fugacity of my solid phase. So if I need to calculate the fugacity of my solid phase, that's just equivalent to the fugacity of my vapor phase, where we've been told that the vapor phase may be treated as an ideal gas. All right? So the fugacity of my vapor is just phi vapor times Psat, where we're told that the vapor phase could be treated as an ideal gas, so phi v is just 1, and all we're left with is Psat. Okay? So the fugacity of the solid then is just equal to Psat, which is that 0.611 kilopascals. Cool. Okay. C. Calculate the Gibbs energy of ice at the triple point. Okay. So now, actually, this is a bad question, right? Why? Because remember, thermo is always just interested in property changes. Right? There's no such thing as internal energy, right? Our first law of thermodynamics, remember, is nothing more than delta U is equal to Q plus W, right? So inherent in our first law is that we're calculating differences in properties, or differences in our properties are what's of interest. We talked about reference states being useful to define what looks like an absolute property, but the issue here is they don't actually give us, a reference state if we were to use that to calculate an absolute G, with respect to that reference state. And so I really don't see a way in which you can calculate an absolute G in C. Okay. And so, I would leave it at that. Or if you wanted to give, feel compelled to give an answer, I would actually say that the Gibbs free energy of ice, right, the Gibbs free energy of, say, solid ice, is equal to 0. Okay. If you were to look at the steam tables in the back of our book, for water, a common reference state is the triple point. Why? Because at the triple point, my system has 0 degrees of freedom. So just in saying that water is at its triple point, the state of that system is fixed. All right, so a common reference state for water that you'll see in a lot of sets of steam tables is the triple point. All right, and so if I were to adopt the triple point as my reference state, well then the molar Gibbs free energy of ice at the triple point would just be 0. Right? So C, I think, is a pretty bad question, unless they were to give you, say, a reference state or ask you to calculate the change in molar Gibbs free energy between two states. Okay. Now D. Okay. Calculate the fugacity and fugacity coefficient of liquid water at 0.01 degrees C and 300 bars. You may assume the density of liquid water is constant and equal to that. Okay. Well, the first thing I notice here is if I compare to B, where we have water at its triple point, right? The triple point's temperature is 0.01 degrees C. Here I'm also at 0.01 degrees C. Okay. The difference is at the triple point, my pressure is 0.611 kilopascals. So here I have a pressure of 300 bars. So I need to calculate the fugacity for a system at the same temperature, but at a pressure greater than that at saturation. Right? So essentially I need to calculate the fugacity of compressed liquid. Okay, cool. Do you remember how to tackle this? Okay, so what should be ringing, hopefully the bell that should be ringing in your head if I'm trying to calculate the fugacity of this compressed liquid, so a system at the same temperature but a higher pressure, what should be ringing in your head is Poynting correction. Okay, and so in case you can't remember Poynting correction or don't remember it, we'll essentially cook it back up or rederive the Poynting correction so you see where it comes from or what the idea is. Okay, but the basic idea is that at the triple point, okay, so at the triple point, okay, we had that FV, fugacity of my vapor phase, is equal to my liquid, is equal to the solid, or I'm just going to rewrite that as, the fugacity at saturation at T, okay, and that's going to be at our temperature of 0.01 degrees C, okay, was equal to 0.611 kilopascals, okay. So now the idea of the Poynting correction is I want to calculate the fugacity of a compressed phase. So I'm going to have a system at the same temperature but a higher pressure. Okay, so the trick is, if I want to calculate the fugacity of this compressed phase, okay, and this will be at C, or at the same temperature T, but at some pressure P, okay, I'll use a superscript C for the fugacity of my compressed phase, okay, I'm going to write that as the log fugacity of my compressed phase at T and P, and then I'm going to use my favorite mathematical trick, which is adding 0, right? Our favorite mathematical tricks are adding 0 or multiplying by 1, right? So that our expression is unchanged. So by add 0, I'm going to add a log F at saturation at T and subtract a log F saturation at T, okay? So this would be my system at saturation at the same T, which in this case would correspond to the triple point. Okay, so rearranging, I get that log FC, okay, is equal to, and I'll drop the functional dependencies for now, okay, is equal to log FSAT plus log FC minus log FSAT. Okay. And remember, the general idea is this is what's going to be my Poynting correction. Okay, and key here is that these two states are at the same temperature, okay, but they're at a different pressure. This is at my pressure of interest. This is at my saturation pressure for that T. Okay, and so how would I calculate this? Well, okay, if you think back to, I believe it was chapter 7 when we introduced fugacity, okay, our definition of fugacity, so I'm going to get on an aside here, just in the interest of trying to explain things fully, okay, and we'll come back here, is remember our definition of fugacity is for an isothermal process, okay, for an isothermal process, much as I have here, that a difference in Gibbs free energy, so G, okay, and so this would be at, say, T and P minus G naught, which is at the same T, and pressure P, pressure P naught, so it doesn't need to be at the same pressure, but needs to be at the same temperature, is equal to RT log F, fugacity of my state of interest at T and P, relative to F naught at T and P naught. Okay, or equivalently, if I wanted to divide through by RT to get in its dimensionless form, okay, it looks like I'm going to run out of paper, so let me add a new page. Okay, so picking up here. Okay, so if I were to divide through by RT to get in dimensionless form, okay, I could rewrite this as 1 over RT G at T and P minus G naught at T and P naught is equal to, this is a 1 over RT G naught is equal to RT log F at T and P over F naught at T and P naught, okay, or playing with my log rules, okay. Well, again, we don't even need to play with our log rules to get this differential. Well, let's do it anyways, okay. Or that would be equal to using log rules, log F minus log F naught, okay. Dropping the functional dependencies just so I don't get cut off. So if I wanted an expression for the differential of log F, okay, what's key is this, essentially reference state or standard state value, okay, is just going to be, constant. Okay, so that what I would end up with is that the differential of 1 over RT G, the differential of my dimensionless molar Gibbs free energy, is equivalent to the differential of log F. Okay, and why this is useful is, remember, okay, we're looking at a process at constant T, an isothermal process. And so if we were to look back to when we introduced dimensionless G back in chapter 5, so if we have constant T, which means that dt is equal to 0, okay, our differential for dimensionless G just becomes V over RT dp. Okay, so why we bring that in, right? We're talking about constant T. So if I were to calculate the log fugacity of my compressed phase at T and P minus log SSAT at T and, it'd be T and, we'll write pressure PSAT, okay, just for completeness, that would be equal to the integral from PSAT to P V over RT dp. Okay, again, this is my Poynting correction. This is my Poynting correction. Right, Poynting correction is just the change in fugacity of my compressed phase relative to that at saturation. Right, it's like a perturbation term. Okay, now the last piece of information, or key piece of information we'll take from the problem set, is we're told to assume that the density of liquid water is constant. Okay, so density here, I have it written as grams per centimeter cubed, right? We know the molecular weight of water, though, is 18 grams per mole. And so, I could very, very easily convert that to molar density, moles per volume, okay? Molar volume, which is just volume per moles, would be, the inverse of that, okay? So saying density is constant would be the same as assuming molar volume is constant, okay? So the significance of that is, in general, if I wanted to calculate this, okay, R and T is constant, since this is a constant temperature process, I could pull that out, but I would need to know how V changes with respect to P in terms of integrating it. But if I assume that my fluid is incompressible, okay, and generally for compressed liquids, assuming that it's incompressible is a pretty good assumption. If you look back at your PV phase diagrams back in chapter 2, so in that compressed liquid region, as long as I'm at temperatures well removed from my critical point, then those isotherms are pretty vertical on my PV phase diagram, indicating that dV dP at constant T is essentially 0. Okay. So anyways, so if we assume molar volume's constant, okay, what that does for me, okay, is I can assume molar volume's constant, so I can pull out V over RT, so then I'm just left with integral of PSAT to P dP, and so I'm left with V over RT times P minus PSAT, okay? And that's my Poynting correction, okay? And so then, if I wanted to rearrange, okay, log FC minus log fsat is equal to V over RT times P minus PSAT. Okay. Playing with my log rules, I can write this as log FC over FSAT is V over RT P minus PSAT. Take the exponential and then multiply by FC or FSAT, and I get the FC is equal to FSAT times the exponential of V over RT P minus PSAT. Okay, bam. All right, so I just as well could have calculated the difference term here, and then if I would have gone up, log FC is equal to log FSAT plus that difference, or it's equivalent to just rearranging that here. Okay, so if I need to calculate FC, okay, I've already calculated FSAT. FSAT was at 0.611 kilopascals. V is the molar volume. So now you're going to have to work a little to get the molar volume, because what we're given is a density in grams per centimeter cubed. So I need to get the molecular weight of water, which is 18 grams per mole. So I can convert that to molar density, moles per volume. Take the inverse, you have a molar volume. Okay, but that's still not quite it, because what you need to make sure is that this whole term is dimensionless. Okay, so P minus PSAT, make sure those pressure and your saturation pressure are in the same units, because you're given pressure in bars, but PSAT's 0.611 kilopascals, so you need to use consistent units for those. And then you need to make sure that when that change in pressure is multiplied by V over RT, it's dimensionless. So what I might do is convert, say, this to pascals. Then I can use R and T and SI units, and then I just make sure V is in units of meters cubed per mole SI, so that everything cancels out and works out. And so then that'll be, so then that'll give me my Poynting correction. Okay, so the units, right, FC is going to have the same units as FSAT. Okay, so this, right, is dimensionless, so this will just give me a number. FSAT I could keep in kilopascals at 0.611 kilopascals, and if I do that, I'll get an FC in kilopascals as well. Okay, cool. So that's the fugacity of my compressed phase, right? And essentially, we re-derived Poynting correction. Remember, the idea with Poynting correction is it's not really, it's rather straightforward, right? In terms of, the key is knowing what it is, right? And then knowing the name Poynting correction is often attached to it. And if you look back in our notes from Chapter 7, where you need to be concerned about Poynting correction is when you're at pressures, much greater than saturation at that corresponding T. So in this case, I'm at a pressure that's, okay, so this is 0.611 kilopascals. Atmospheric pressure is 101.325 kilopascals, okay, which is equivalent to 1.0125 bars, okay? So we're interested in a pressure of 300 bars, right? So this is going to be huge. So it's going to be much larger than the corresponding pressure of saturation, so Poynting is going to become important and necessary. Okay. So important thing with Poynting correction is knowing what it is, what it corresponds to, where it comes from, and then that name Poynting correction is attached to it. And when I'm going to need it is when I'm dealing with calculating fugacities of compressed phases. Okay, phases at the same temperature but a pressure much greater than at saturation. Okay, because it could apply to solids as well if I have compressed solid. Okay, but getting back to the problem, that's fugacity. We want fugacity coefficient as well. So if I want the fugacity coefficient, well then I just need to play around with my definition of fugacity coefficient, right? Because if I were to expand out the fugacity of my compressed phase, I'm just trying to grab my pen here, fugacity of the compressed phase, right, is by definition the fugacity coefficient of my compressed phase times P. Okay, it's a pure system, right? So I don't need a partial pressure term. It's just P. Okay, so therefore, Vc would just be equal to FC over P. Right? There you go. Boom. Okay. And that's it.